So the lecture 4. Yes, so the previous lecture we demonstrated the first algorithm. It was quite artificial. Yes, and actually the goal was just I was speeding up the course to be able to present the first algorithm as soon as possible. So I was introducing the minimal set of notions which is needed for this. And now we start to do systematic structure, systematic studies of what you can really do on a quantum computer. So one or two lectures, so two lectures would be devoted still to, how to say, theoretical observations. And at some moment I will show how to quantum computer and internet, yes, how to make all of this which I show on the screen also possible to run either on a true computer if you are able to register at IBM or simulator if you are not able to register in IBM. By the way, does someone manage to register in some of the systems? Did someone try?
Sorry, register where?
In IBM Quantum Experience.
Oh, I didn't try.
Yeah. So just try, because I'm telling. So I was registered there a long time ago. Yes. So and my account is still good. Yes. But the problem is that they are constantly changing the rules. Yes. So, and for example, they changed it in January. Yes. So after New Year, they definitely changed them. So I tried to register a new account and I see that the rules have changed. Yes. And so please check that you can really do this, because this depends on the country, on are you student, professor, which mail you are using. So, and if it doesn't work, try also to register from incognito. Yes, so kind of.
Sorry, what's the name of the website?
So search IBM Quantum Experience.
Okay.
Yes, and there was a link to there there was a better description on the slides of the first lecture.
All right, thanks.
Yes. So, okay, so let us go to systematic study. So just a second. I promised that I start with 1 qubit gates, but I will actually start with one more notational remark. Yes. So why I use this type of notation for qubits? Yes, so there is a reason. Yes, it's not mathematical theorem, but there is a philosophical idea underlying. So this is related to Dirac notation, or sometimes it's called Bra-ket notation. And bracket, you should, even that it means brackets, yes, but you should separate, two parts, bra and ket. Yes. So what formalism I use? Yes, I write psi as A0 plus B1 and consider it as a vector in a C2 space. And remember, vector is a column. Yes. And let us consider conjugation. Yes. And the conjugation, which I sometimes will denote with a star and sometimes with a bar on top. Yes. So the conjugation to a column should be a row. Yes. So this is in a yes, it's a transposing kind of, but in linear spaces there is a notion of conjugated spaces. Yes, and the conjugate space is in a certain sense consists not of columns, yes, but of rows. Yes, and okay, you make a complex conjugation of those numbers and transpose column into row. Yes, and I would like to have a notation for this. So for this row of complex numbers, yes, also in the style of notation of quantum state. Yes, it's not a quantum state, it's something different. Yes, and I will write it so when I had a quantum state psi with direction to the left, to the right, yes, then I would consider, I will denote it like this. So kind of I first close the bracket and after this write a vertical line. Yes, so like this. Yes, and I also will use it for 0 and 1. Yes, so still I can write it in a such form. And so 0 and 1 should be considered as rows. Yes, and the A bar and B bar are complex numbers. So I still use the linear form. And in that case, for inner product, yes, for scalar product, I mean, it's not a scalar product. A scalar product is something what is between two vectors, yes? But this is inner product. So I write it like this, meaning that the first vector is multiplied on a first row is multiplied on a second column, yes? And in that case, I have a notation, a row multiplied by a column. And thinking that this is a matrix 1 by 2, and this is a matrix 2 by 1, yeah, so they should give you a matrix 1 by 1, so a number. Yeah, so this is the philosophical notation. And such type of considerations, so they would appear actually not in the beginning of the course. Yes, so they would appear for advanced algorithms. Yes, so I will use them. Yes, in the beginning, I mean, this is just a notation, not really needed. Yes, but this is a convenient story, and this is the motivation why people write like this. Yes, and in that case, oops, so I missed. So this is vector, and this is covector. So it's needed to change. Yes, and the bracket. Yes, because this is bracket. Yes, yeah. This is, yes, this is the covector, and this is vector. Yes, column is vector, row is covector. Yes. Yeah, so misprints are always exist. Yes. And this is why it is called bracket, yes, because it looks like that I just write a scalar product in brackets. Yes, and I kind of glue those two vertical lines in a single one. Yes, so this is notation. It comes from physics. It comes to what is called generalized functions. If you come to theory of partial differential equations, and I don't know what was introduced earlier, who take the notation from whom, yes. Certainly quantum computer takes it from quantum physics, where people also do like this, yes, but yes. Okay, yes. So this was what is called inner product, yes, but there is also outer product. I can multiply them in opposite order. And in that case, I multiply column by a row. Yes. And in that case, I will get matrix 2 by 2. And here it is, and I hope I multiplied it without misprints. But please, more trust to this notation rather than to this notation. Yes. And so what we have, inner product is a matrix, is a number, and the outer product is a matrix, so it is an operator. Yes. Because actually, because I write it in this vector covector notation, it would be just an operator. I don't need to fix the basis. Whatever basis I choose, in whatever basis I do this calculation, the operator would be the same in the end. Yes? So this is an operator. Yes? So please think about this. And this would be super important for the second part of the course, in the moment when I would consider quantum computers with errors. Kind of such type of operators would be representing the states. Yeah, so I would, instead of vector, I would consider operators of these styles. Okay, yes, I showed this for 1 qubit in very details, but in multi-qubit system it is the same story. Yes, so if I would like to consider conjugation of vector, I can write it in such form. And then it would be just the sum of the conjugated coefficients times covector. This is a new notation. Yes, so this is not this is a definition. Yes, so this is not a statement. This is a definition. And then if I want to find the inner product, yeah, so I multiply one covector to other vector. Yes, I just summate coordinates, summate multiplication of coordinates. And this I could think that I just open this bracket and use the formalisms that K scalar product of K and J is equal either 1 when K is equal to J, yes, or when they coincide, and they're equal to 0 if K is not equal to J, yes, which corresponds that this was orthonormal basis, yes. So if I would like to use the notation of bracket notation to write sums like this, I can write it in arbitrary basis, yes. But in order to make scalar product, this basis has to be orthonormal. Yes, so this is the story. Yes, so you can write like this. Yes, you can write like this, not only for basis vector. So I write like this here. Yes, it can be anything. But the meaning, what exactly it's opened with a complex numbers, yes, if you want to represent it as a line of complex number, you need to fix an orthonormal basis. So you cannot take arbitrary basis. Yes, you have to work with orthonormal. Okay, yes. So now, yes, so this was a notational remark. So now let me move to really a kind of theory, and today I will speak about 1 qubit gates and 2 qubit gates. Yes, so what is acting on 1 and 2 qubits. And even that I told, yes, in the very beginning, yes, I told that what basic operations are possible, yes, is determined by a physical device. Yes, and different physical devices has different basic operations which they implement. But in the theory of quantum computers, yes, by some reason, kind of people do not rely on this. Yes, but while in classical computer, everybody relies on or and and. Yes, so it's kind of written down into the whole theory. Yes, and here it is not written down which gates exactly are in the beginning. It would be clear in the end of this lecture. And the long story short, I mean, there are relatively small set of operators of 1 and 2 qubit operators, such that if you implemented them, then as a composition of them, you can implement any 1 or 2 qubit operation. Yes, and basically all the computers which are present now create certain set of basic elements which allows you to create anything. So kind of when I develop algorithms, and my goal of this course is developing algorithms. So for me, it doesn't matter. Yes, because I would operate that, okay, I can do any 1 qubit gate and any 2 qubit. Yes, but let me show the mechanism how it is happening, because devil in details. Yes, because it's also, it would be not important for 1 and 2 qubit gate, but later I would extend for multiple qubit gates. And there is a detail. Yes, so when I speak about, say, certain operation on n qubits, and I can decompose it into basic operation, it's still important how long is this decomposition. Yes, because if this decomposition is 2 to the power n, yes, I mean, then I lost advantage of quantum computer. Then why I need it? Yes, because if it is a long procedure, then I lost it. So philosophically, we need to know how it can be decomposed into basic stuff. But okay, let me do something. Yeah, so, and by the way, so this would be not typical for mathematical course. A lot of statements I would just formulate and will not prove them. Yes, I suggest you please trust. Yes. So the general one-qubit gate is ABCD with ABCD complex numbers, not any for numbers ABCD forms a unitary operator. Yes, because we need to have here unitary operator. But let us see certain fundamental and why everything. So first of all, we already saw not operators sending 0 to 1 and 1 to 0. And second, we saw Adamar gate. Yes, this is this matrix. Yes, but it is more important just to remember that it sends 0 to normalized sum of 0 and 1 and send 1 to normalized difference of 0 and 1. Because it is would always used actually kind of to create a normalized superposition state. Yes, so when you have 0 plus 1, or as we did in previous lecture, yes, we did 0 plus 1 plus 2 plus 3 plus 2 to the power n minus 1. Yes, just where all the possible states are with the same coefficient. Yes, it is very often just used for this. This is a very good approach. Yes, and I forgot to write this, and I also forgot to write it on the presentation, and both of them satisfy important property. That if you apply 2 times x, yes, x of x, you will get identity. So you will get the same. And the same is true for Adamar. Yes. Because like we can make a calculation. Yes, so let us do it. Yes. Actually on a blackboard. So one. To where goes 0? Yes. After the first Adamar, it goes to 1 over square root of 2, 0 plus 1. Yes. And after second Adamar, it goes to 1 over square root of 2, 1 over square root of 2 of 0 plus 1, plus 1 over square root of 2 of 0 minus 1. Yes, because I applied here Adamar and applied here Adamar. And we will see that the 1 cancels. And actually, okay, after this, you have to multiply properly all the things made. Yeah. 0. Yes. But actually, you don't need to multiply and summate because you know that this is 0, yes, times something, yes. Oh, okay, no, it potentially could be something complex, yes. So that, okay, you need to calculate and get 1, yes. You can get minus 0 as well, yes. And where goes 1? Yes, it goes to 1 over square root of 2 of 0 minus 1, yes, which will go by Adamar to 1 over square root of 2. And let us more carefully look. So this would be 1 over square root of 2 of 0 plus 1. Yes. Minus 1 over square root of 2 of 0 minus 1. Yes. And here cancels 0. Yes, but what is more important, so I multiply this 1 over square root of 2, I get 1/2. Yes, but here I get a positive story. I get 1 minus minus 1. Yes, I have 2, 1. Yes. So this is 1. Yes. So both of them have a square identity. Yes, which is nice. Yes. Okay. So next. So there are 4 matrices, which in all the cases they are implemented somehow, but I cannot actually explain right now why they are so important. But this is, they called Pauli matrices, and these are matrices which are at the same time unitary and self-adjoint. There are not so many such matrices. Yes? And so this is those matrices. And I will never use this in the course, but also actually those 4 matrices, yes, form a basis in the space of, in linear space of all self-adjoint operators. I never kind of, you can represent any self-adjoint operator as a linear sum with coefficient of those matrices. But I will never use it in the course, but this is why they actually are important inside the life, inside the course. Yes, but remember those matrices because they have a notation for them. Yes, 1, okay, is identity is 1, not is called X. Yes, X gate. This is Y, so minus II, and this is Z. So it has on diagonal 1 and minus 1. Yes. And a special importance for this is the role of them as a self-adjoint operators, not only as unitary. Because if you consider them as a Hamiltonian, yes, then you will get gates which actually would be the basic blocks for a lot of stuff. And this is a rotation, so-called rotation gate. So you consider just exponent, yes, so that's, remember, yes, so that's, I wrote it in a mathematical form, e to the power minus a I h. Yes, I can write all the unitary operators in such form. Yes, and under this h, I start, and where h is self-adjoint, I consider those basic, those Pauli matrices. And I mean, they're called rotation matrices. Yes, if you are not comfortable with exponent of matrix, which is fine, just you can think that there are those formulas. Yes. So here it is just a rotation on a plane. Yes. So you kind of do independently rotation in real parts and independently rotation on complex parts. Yes. Here, okay, you kind of mix them. Yes. So that I think one of them should be without minus. Oh no! Both should be with minus. The product is minus 1. So product of those 2 numbers is minus 1. This should be. So it's correct formula. And so this is kind of rotation which mixes real part and imaginary part of the coefficients on the plane. Yes. And so this part, it multiplies 0 and 1 on a different coefficients. Yes. And you can also think about this because remember, this was a philosophical argument that you can multiply the state by a constant. Yes. This means that kind of you can keep one of them constant, or like the same coefficient, and another multiply on a certain value. Yes, but it is more convenient to write it in such form. Yes, so you can also look. I mean that this thing, yes, means that you also can implement something like this. Yes, the operator of this form. Yes, and Yeah, so this. And typically, yes, those gates are implemented, yes, in the quantum systems. So because you have these Pauli matrices, which are basic blocks of everything. So, and if you can implement them as an energy operator, you can implement these notations, those rotations. So the last operator corresponds to identity. This is just adding a constant, multiplying both coefficients by a constant. It seems that it's doing nothing, yes, because it moves a state to an equivalent state. That this would be a part also of more complicated operators where it would be not like it's not correct that if two operators is equivalent, then the certain advances of them is also equivalent. Yes, so I would introduce such operations. Yes, so because of this, let's remember. Yes, and what is true is that actually it's a theorem, mathematical theorem, but I would not prove it. Yes, because I mean, for the quantum computers, the proof doesn't matter. I mean, it's an argument which you need to do. It's a long technical, but which tells that okay, any operator U can be represented as a composition of Z rotation of this phase shift, yes, on multiplying on a constant. Z rotation, no, I read it from left to right. Z rotation, Y rotation, Z rotation, and the multiplication to equivalent. Yes. Z is this guy, yes, roughly speaking, that story. And Y is something inside real. Yes, we do not use the, for example, yes, how it can be represented is that the way how, so here I wrote the way how the X rotation can be represented in this form. Yes, you use Z rotation for minus pi over 2, Y rotation, and after this Z rotation again. Yes, so this, I mean, I would not check it on a blackboard. Yes, so please trust that some formulas like this are correct. And I think you will tell thank you for me that I don't show those multiplications. Because I mean, you can do this, yes, but people have done it for you, yes. And I mean, it doesn't matter because all what you should remember is that any one qubit gate can be represented as a composition of Z and Y rotation. Yes, and okay, this phase story as well. And that's it. And there is no need, yes, to do more. Yes, so that's you don't even need for future to remember what is exactly the sequence here. Yes, it just if you implemented Z and Y, you implemented Z and Y rotations, you implemented everything. Yes, so kind of this is the philosophical story.
And that U would be a matrix of A, B, C, and D.
Yes.
Those A, B, C, and D are the things.
Oh no. Sorry. No. They do not coincide. Moreover, here A, B, C, and D is real numbers. Yes, and they were complex numbers. So thank you. I will actually change the so you by some reasons after all those years you are the first who point this out, and but I completely correct with you. You are completely correct. Yes, that it's abuse of notation. Yes, so this because U was ABCD. Yes, and those ABCD do not coincide. I mean that's mathematical statement for any unitary operator U. There exist four real numbers A, B, C, and D, such that this is true. Yes, but I actually don't know, yes, how to find from the elements of matrix U the values of A, B, C, and D. No, the general story that how to say, you need proper, so you have bases, yes, to, why there are 4 numbers, yes, because you have bases and it is moved onto orthonormal basis. Yes, and if you count how many such possibilities are, there are 4-dimensional possibilities for this, yes, that keep them orthogonal and 4-dimensional real possibility, yes, because it would be 8-dimensional complex, but after this you have the norm is equal to 1, the angle is 90, yes, so which gives you 4 conditions, so this is 4-dimensional story, and you just need, how to say, that 1-to-1 to match the coordinates, yes, basically. And but the formula, so the formula is easier written not in terms of A, B, C, D, yes, but it's in of the elements of the U, but of the properties of this basis, yes. Okay, yes. So and X, rotation of X can be represented in such form, yes, and this is just an example. So actually, there is no need for this concrete formula. Even that you see here, there is a story that for Z rotation, the angle is quite easy. Yes. And this is also could be considered as a conjugation. Yes. Because you see here the minus angle. So those 2 matrices, yes, those 2 operators are inverse of each other. Yes. So no, you see, you cannot cancel them, yes, because you cannot cancel them because those operators do not commute. Yes, you cannot change the order of them. Yes, so this is very important concept. Yes, so not all 2-by-2 matrices commutes. Yes, so I write it in this order, and they cannot change the order. Yes. And but it tells that rotation over X and rotation over Y, yes, are conjugate. Yeah, so that's okay. Yes. So long story short, any 1-qubit gate is possible if you can realize rotations. So I told that not all operators commute. Yes, it has an important implication. Yes, so first of all, for any operator, there exists square root of this operator. Yes, because any unitary operator can be like philosophical, yes, can be represented as an exponent of I Hamiltonian. Yes, and if you write exponent of 1/2 I of the same Hamiltonian and multiply it onto itself, you will get U. Yes, so that's any operator has a square root, and actually 2 square roots, yes, because you can put, no, you cannot put minus. Yes, you cannot put minus here. Yeah. So that's, but still, it should be 2 square roots. Because you can write minus here, yes, in front. So that's, no, this is, so you have at least 2 square roots, but I mean, theoretically, it could be more of them. Yes. For what? Yes, plus one of each of them. Yes, 4. Yes. Yes, and for example, for not, I mean, there, this is how it looks like. It doesn't. Yeah, it's just illustration that it exists. And for what this slide is created, so first of all, because somewhere in the course it would appear square root of the operator. Yes, and I would like to explain why it is possible to have it. Yes. And the second thing, that don't think that square root of an operator is something easy. Because if you have U as an operator and you represent it as a certain scheme, yes, you cannot immediately write a scheme for a square root of it. Because it's not true that square root of product two operators is product of square roots. yes, because they do not commute. Yes, so just if you multiply this guy by itself, there would be no cancellations inside. Yes, so when I write square root of u, that means okay, it exists, very good. Yes, but still we have a job to think ourselves how to implement it. Yes. That's all with one qubit gate. So maybe you have a questions. This would be very nice to ask.
Sergey,
Yes.
so I'm not sure. Can you explain again more about the intuition, or like what would we use the square root of an operator for?
No, later we will use it for construction of multi-qubit operators, yes, and how we will reduce. So we would consider, I don't know, 4-qubit operation, and we would like to reduce it to 2-qubit operations, yes, and at some moment there would be square root of operator would play a role.
Okay, got it.
So on a level of 1 qubits, it doesn't matter, yes, because of the previous. Everything is possible, yes, and everything is possible in a sequence of 4 basic operations, yes, and because kind of it's whatever we need, it's not more than 4 other operations. So when I write my scheme with any 1-qubit operators, if I would decompose it into basic elements, it would not become more than 4 times longer. Yes, so that's.
Wait, but what do you mean by any gates possible? Like when you have 2 qubits, is it true that you like not every unitary operator works?
So I mean that's whatever operator I invent for myself. Yes. So I decide that I need some operator. Yes. And the question, can I really run it on quantum computer? And the answer is yes, because typically I am able to run any of those operations. Yes, though I have 4 operations here. And if I can run them, then I can create a scheme for any 1-qubit operator.
Okay, so it's like you know that these basis operators work on the computer, you can run them. So if you can represent them, your operator using them, then you know that they will run as well. But that isn't necessarily true for when you have like a 2-qubit operator. You don't know if it will necessarily run, necessarily have those operators under them. Is it correct?
Yes, kind of. We would not, think a lot about how to execute this operator because we know that it can be executed in those elements. Yes, and usually when you go to any platform, yes, say IBM, yes, they would automatically do such a composition and to the gates which are the best for them. Yes, so kind of they would decompose any 1-qubit operation to the best physical implementation by themselves.
Okay, thanks.
So that's it. Yes. More questions about 1-qubit operations?
Have this, we will meet first, like, U2 by U1, and then use this code.
Yes, I mean this because I look on this as a mathematical notation. Yeah, so this is an operator. Yes, so kind of the idea is the following. So if you want to have a square root of the product of 2 operators, you need to think how to create its square root of. Yes, you cannot get it automatically. Yes, kind of. Yes, so you cannot go back to the single basic operations, yes, and make square root there. Yes, be aware of this. Yes, this is just a caution. Yes, and I mean, because there is no good way to do this, I leave it as just a caution. Yes, so please, I mean, please be worried. Yes, so that's. I mean, one of the ideas of the first lectures, yes, before I go to true algorithms, yes, is just to give you a certain intuition, yes, what is easy and what is not easy. Yes, so for you not be confused and looking on this thing, asking the question, okay, but why he is doing here such a complicated step, not just doing something simple, yes? Why he cares about this at all, yes? Okay, so let's have a lot of messages. Let me check if there are super important among them, and if no, then just continue. So, okay, now this I can reply after. Okay, so let us go to 2 qubits gates. First of all, why we need them? Because without, if we live only with 1 qubit gates, then if we start from a direct product state and all zeros is a direct product state, then we will stay in a category of direct product state. Yes. And in that case, we actually would not be able to get advantage of quantum computing. So without more than 1 qubit gate, you cannot be better than classical computer. So we need that. And the most popular and the most important 2 qubit gate is a controlled NOT gate. It works as following. So it acts on 2 qubits, yes, and presuming that you initially you're on a basis state, so A and B are basis states, yes, so that's either 0, 0, 0, 1, and so on, then it never changes A, yes, just the first qubit stays as it is, yes, and the second qubit implement the logic. So if A was equal to 0, then it doesn't touch it. And if A was equal to 1, it replaces B by a not B. Yeah, so this is how it works. 0, 0 goes to 0, 0. That's because first never changes, and the second should not change because first one is 0. 0, 1 goes to 0, 1 because if first is 0, then it doesn't change. 1, 0 goes to 1, 1. First qubit preserved, and the second changes. 1, 1 goes to 1, 0. First is preserved, the second change. And this is the matrix which corresponds to it. Yes, on the first block you have identity, on the second block you have not. Yes, and this is how it works. And please remember this operator because this would be a cornerstone of the course. Yes, this is the element how we implement logic in quantum computers. Yes. So, okay, basis states it also works like an oracle. Yes, similarly to oracle, I can write it in such form. Yes, so. And remember, so if I define an operator on a basis states, I define it for every state. Yes. What? No, it's not correct because this matrix is 2 by 2 matrix, is 4 by 4 matrix. This is 4 by 4. And PH of delta was 2 by 2 matrix. Okay.
like list
Hmm.
with another list?
I would not, I prefer not to consider it in such form, yes. Even that I understand that, okay, the matrix PH delta is not very good, but I told also that it is PH delta is equivalent to 1 e to the power I alpha, yes? And you can ask yourself, yes, why for me not to consider e to the power I alpha equal to 0, 1, 1, 0, yes, and such alpha exists, but now alpha becomes not a number, but it becomes not a number, but a matrix. Yes. I think it's, how to say, not very well fits to the logic of quantum computers. Yes. Because the main idea here that all the previous things which I presented, yes, they were preserving direct product states. And this one would not preserve direct product states. And this is exactly the next line here. Yes. So if I start with 0, 0, I apply Adamar to the first qubit. Yes, so I will get a state like this. And after this, I apply C naught to those two qubits. Yes, no, C naught, it acts on two qubits. Yes, so that's so to both, yes, because there is no other possibility. Because this is, I don't need, so here I need to write tensor identity. Yes, but here I don't need to write because this is already an operation on two qubits. Yes, and then it will move 0, 0 to 0, 0, and 1, 0 to move to 1, 1. Yes, so this would be such. Yes, and such state is not a direct product state. Yes, so that's it shows that, okay, using this operation, I am able to create not direct product states. I'm able to create entangled states. Yes, we call entangled is not direct product. Yes. So now with this guy, I potentially can get a quantum advantage. So there is a trivial generalization of it. So why I use controlled not, why not controlled U? Yes. So with the same logic, the first qubit never changes. And to the second qubit, if A was equal to 0, then do nothing. And if A was equal to 1, apply U. Yes. And in that case, its matrix would be like this. Yes. And notation is CU. Yes. And on strings, yes, I would draw it like this. So here there is a field dot, big field dot means that this is control. So this is A, and here is U. Yes, the operation on a second. And for not, because this is very often, very frequent operation, it has a special notation like this, because in that case, kind of this line goes over here, so kind of you can first draw a line, yes, and after this you do like this, yes, so you don't need to erase anything, yes, so this, because it's so frequent that people would like to have a notation which make it easy to write. Yes. Yeah. Yes, 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 of course. Of course. I mean, when you speak controlled U, you should specify which qubit is the first and which qubit is the second. And I mean, you have potentially have a system of 100 qubits, and you can say that the first is 11th and the second is 32. Yes, so that's.
And if we there in our the LV and Q.
Yes, so it's it's, you see, this ID U, or, yes. So, and you should, if you are in a 100 qubits, you should multiply to 98 identities. Yes. So as I told you, I would never, how to say, I show those matrices here, but I would never use them in calculation. So for calculations, I will use these rules. Yes, exactly because of what you told. So that's starting from 5 qubits, it would be 32 by 32 matrix. I mean, sorry, I would not write 32 by 32 matrix. And say thanks to me, whatever is exam or homework, I will not ask you to do this. Yes, so that's. Yes, so the other thing, yes, which it's not only possible to change order, but it's possible to control not by 1, but by 0, yes, which tells that I don't change the first, and I apply operator U if A was 0. Yeah, so such mark, yes. And it's also common operation. So for this operation, we just draw here an open circle, yes, not a full circle, not full dot, but dot with empty inside, yes, and it is equivalent that if I apply not, just move A from 0 to 1 and from 1 to 0, apply controlled operator and apply not again, yes, okay, reverse A to the original state, yes. Yes, yes, it would be like this. Yes, so if I would like to say control, yes, I would just draw like this. And this would be common notation, so just I do this more just for you to prepare. Yes. And okay. Two qubit gates. Yes. If I have a controlled U, yes, and I know that controlled U can be written as a composition, or U can be written as a composition of Z, Y, Z rotations, certain coefficient in front, yes. So then I could actually implement control U as a 1 qubit operations and control nodes. And this is the exact formula. Here, BCD, ABCD corresponds to ABCD here. So I will also upload to the group and on the website the scanned version. Yes, so I not only have a presentation, but I have a text which I write for myself. Yes, so I not type it, but I at least write it. Yes, and there I will show how to calculate this. I mean, because I mean this is a direct calculation. Yes. And that, so it is well-defined object, well-defined object, why they act the same on all basis vectors. Yes, so this is this. What? No, not on this triangle. Yeah. So this triangle, no, this is not an empty operation. Yes. So this triangle is 1 qubit operation. Yes, and this is diagonal of 1 and the exponent. Yes, so this is 1, 0, 0, e to the power 8a. So it is this one. Yes, yes, yes. But this is not what I call the pH of delta. Yes, so it's slightly different story. Yes, and here you see I have certain A is just rotation, Z rotation, but B is a composition of Y rotation and Z rotation. Yes, and actually all those guys are combined in such way that if I would have here 0, let's look at it. If I have here 0, then delta would act empty. Yes, it doesn't do anything. Yes, and control not also will do nothing. Yes, so if they construct in such way that A, B times C will give you identity. Yes, because if the first qubit is 0, then it should give you nothing. Yes, and if the first qubit is 1, yes, then so here will be not. So I would put here not, put here not. Yes, and it constructed in such way that AX, A not, B not, C would give you U. Okay, we will give you this part. Yes, and this part will give you this coefficient. Why? I mean, the question is why? I mean, because I specially chose those things here. Yes. And there is no, how to say, good answer. Why? Yes, it's just the general idea that kind of we need to say, okay, we have U, yes, and we want to represent it in a form A. We want to find such A, B, C, yes, such rotations that their product would be identity, yes, A, B, C. So actually not ABC, it's CBA, yes, because we first apply A, after this B, and after this C, such that CBA is identity, yes, and C not B not C is equal to U. Yes. It's a multiplication. This is one qubit operation. This is one qubit. Yes, and this is what is happening with the second qubit if the first one is equal to 0. Yes, kind of 0 pi, yes, would be mapped to 0 CBA pi. Yes, and a 1 pi would be mapped into e to the power a. Yes, it would be mapped to the e to the power ia1, and the c not b not c oops a. Okay, now I got your question. Yes, a. Yes, sorry. Yes, pi. Yes, and we want this guy together, yes, to be equal to U, yes, and this guy to be equal to identity, yes. And I just spend careful time, yes, to find, and okay, not actually me, yes, other smart people have found the time which rotations I should put where, yes, in order just to have those two equalities correct. What? Because none of control nodes acts. Yes, so this is empty things. Delta also acts by this element, so it doesn't change it. Yes, and phi, you first apply A, after this, you do nothing with it, apply B, do nothing with it, apply C. Yes, so A, B, C. Like in matrix, if we first apply A, after this apply B, after this apply C, we write it AB, like CBA, not ABC, because we open from right to the left. Yes. And the key element of the proof, is the statement, yes, which I have here, such type of structure, yes, that not times Ry theta not is equal to Ry of minus theta. Yes, and not Rz theta not is equal to Rz of minus theta. Yes, and I have notes, and I mean, I need to do the proper conjugation. Yes, so just, yes. Okay. Arbitrary gate. Arbitrary 2-qubit gate. Arbitrary 2-qubit gate can be written in a such form, where just these blocks A1, A2, B, C, D, A3, A4 is a certain 1-qubit operations. Yes. Please, so even that for the proof of how one can explain why any 1-qubit operation can be decomposed, I myself looked. Yes, for this proof, I even didn't look. Yes, so but still I believe it. Yes, so any 2-qubit operation, so any matrix, any unitary matrix 4x4, yes, can be represented in a such form. And philosophically, for me, this means only one thing, that any 2-qubit operator is possible. Yes. And because any 1-qubit can be represented as a composition of rotations, yes, in the end, any 2-qubit operator can be represented as a composition of rotations and CNOT. So if I manage to implement those operators, and all the platforms which exist can do this, they can implement any 2-qubit operator. Yes, and this is kind of long story short. Yeah, so if you didn't like my lecture today, then please remember this one statement. So if you can implement rotations and control knot, and okay, you need to understand control knot. This is mandatory. Yes. Then you can implement any 2-qubit operation, which is your favorite. Yes, so long story short. Long story very short. It's even not a slide, it's a half slide. Yes.
A1, then B, then dot, then A3.
No, we will do the following. Do A1, A2, and it doesn't matter in which order. Yes, you will get it in always the result. After this, you do this controlled knot where you is controlling by the second qubit. Yes, and apply to the first one. After this, you do B and C, and not important in which order. After this, you do once again control knot, you do D, you do control knot, and you do A3, A4, not important in which order.
So if this is right, and the same point that you put there, we could say like A4, A3,
so we will start. So we have a state psi, yes, which is 2-qubit state. Yes, I will write here. Yes. And it would be mapped, yes, and I keep places here. And when I write A1, let me first apply A1. This is A1 tensor identity. Yes, after this I apply A2. Yes, this is identity tensor A2. Yes. After this, I apply C naught. Yes, and I will put coefficients because the first is 2, second gate, a second qubit, and after this, the first qubit. Yes. So I need to have 2 coefficients. I need to specify on which qubits. Yes. So after this, I do. Now, for the next step, let me just show another notation for this. Yes, I will write B tensor C. Yes, because if I apply A1 times tensor identity, and after this identity tensor A2, this is the same as I apply A1 tensor A2. Yes, so this is, because of this, I just write it like this. Yes, and after this, you write C naught 1, 2. Yes. After this, you do identity tensor D. Yes. You do, so that's, yes. You do C naught 2, 1, and you do A3 tensor A4.
Correct. Which is the
First is this, so first is this, and second is that one. And when you will go to any of those simulators, yes, which any of these environments like IBM quantum environment, so they will have either it's drawn like this, or it would be somewhere short text, yes, which represent, the scheme. And then when you will write C naught, usually it is written as a CX, yes, because naught is X, yes, so CX is shorter, yes, and it would have a parameters, yes, and parameters would be on which qubit you put the dot and on which qubit you put naught, yes. So this is long story short, but this is not the end of the 2-qubit story, because there are 2 more things. So first of all, there would be certain important 2-qubit operations. Like one is like all are important, but some of them are more important than others. Yes, and also I would like to introduce a notion of semi-classical gates. So this is the next slide. Yes, semi-classical control operator. Assume that we have a scheme which is written like this. So we have a certain some operator here, yes, so to be able to create any state. And after this, we do the following. We measure the first qubit. We get in our classical world, in our classical computer result, 0 or 1. And if we get 1, we apply to the second qubit operator B. Yes, so this is logically, yes, so I draw it like this, yes? And this means that if result is 1, yes? And the question is, so I will write an analogous scheme, yes? I just assume that before the measurement, I apply control V operation. Yes, which also works in the style. If the first qubit is 1, then I apply V to a second qubit. Yes? And the question, would they be equivalent? So does it matter how to do? And the question to the room, yes, what do you expect? To room or to the Zoom? You think yes. So are those two schemes equivalent? So if you first measure and depending on the result, apply V, or you first apply controlled V, which is the quantum version of if operator, yes? And after this measure, would the result be the same? So no, but I have measurement in both cases, yes? And what means equivalent? Yes, equivalent means, okay, I go to the next slide. Yes, okay. So what is the result? Is the value 0 or 1, which we get, and the state of second. Yes, and they are equivalent if the distribution of the value 0 or 1 is the same. And if we got the same answer in those two, so the probability to get 0 is the same. Yes, and if we get whatever we get, so if we get 0, then the second qubit would be in the same upside. It would be in the same state as it was. If we get here 0, the state here and here would be the same. And if we get in both 1, the state here and here would be the same. Yes? And they're equivalent. So you were right. Yes, they're equivalent. And let us do the calculation. So if we use this scheme, yes, if we use this scheme, then okay, I think that we started with A0, I0 plus B1, I1. So I wrote it in a form which is nice for measure. Then with probability A squared, I will get 0 and the state 0, phi 0. Yes, and in that case, I mean, I don't need to do anything more. So this is my final. Yes, and if I get 1, which happens with probability B squared, my state would be 1 phi 1. But in that case, I also need to apply operator V to the second qubit. Yes, so it will, the state, the final state, be 1 V phi 1. Yes, so in the end, so with probability A squared, I would be in this state. With probability B squared, I would be in this state. Where? Where?
In our answer.
So in our answer, yes, yes. So it would be like this. And if we do the second scheme, yes, so what we will do, we first apply controlled V. And on this term, it is not changed because the first qubit is 0. Yes. And the second qubit, yes, we need to apply V to phi 1. Yes. So it would be this state. And now we do measurement. Yes, and we will get 0 with probability A squared, and then we get this state. And we will get 1 with probability B squared, and we'll go to this state. And yes, if we got 0, the states coincide. If we get 1, the states coincide. Yes, and probabilities are also equal. So it seems that this operation, I mean, doesn't give us anything new. And this is a reason why, I mean, in all theoretical works, you will never see this operation. Because, I mean, it can be replaced by existence. Yes. But on practice, of course, there would be a difference. Because, as I told Here I measure 1 qubit and do 1 qubit operation. And this is usually very good implemented. It's a high quality on the quantum computers. And if I do this thing, yes, this is a 2 qubit operation, which would be implemented on a physical device with much lower quality. So theoretically, they're equivalent. On practice, this will give less error. Less error. Yes, so there would be a few less errors. Yes. So certain special qubit operations, and please consider this now as a descriptive story. I would just don't see logic in the order or something like this. I just say operator by operator because they would be appearing somewhere later in the course. First of all, control sign, yes, the sign operator. So you can think about, so we remember the Z operator, yes, it's controlled Z. Yes, if, so this is the matrix which corresponds to it, yes, and kind of in this block it is identity, and in this block it is that operation from Pauli gates. Yes, so I introduced Pauli gates at some moment. Yes, this is that from there. Yes, and from one point it can be used instead of control nodes. Yes, so this is those two schemes are equivalent. So if you do on the second to be rotation y minus p half, apply control sign, and use rotation of y p half on the second qubit once again, then it would be the same as C naught.
So,
So for 1, 1.
yeah, y at 1, 0. Yeah.
Yes, 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 yes. No, we would also interchange those. We will also, so we will get an operator, yes, so which I practically telling here, yes, is that if I look on a controlled node, yes, which is 1, 1, 0, 1, 1, 0, yes, and let me blah, 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 yes, then it would be equal to this thing, yes, so I apply Ry to the second qubit, yes, and this would be identity Ry, yes, and let me see how it works in a so let us see 0 so 0 phi, yes, will go to 0 Ry of phi, yes, and 1 phi will go to 1 Ry of phi. Yes, so this matrix, yes, would be the following: Ry of minus p over 2. So, and this is 2 by 2 matrix. Yes, so here would be zeros. And here would be also Ry of minus p over 2. Yes, I don't remember what is exactly the matrix. Yes. After this, I do control sign. Okay, so I write it. So this is, let me first write, and after this, I will comment. Yes. Ry of minus pi over 2, 0, 0, Ry of minus pi over 2. Yes. I first apply this operation. Yes. So it comes to the end. Yes, after this I apply Control Z. After this I apply this guy. But please, please, I never will multiply those matrices. Yes, I will always do it in the following, in this form. Yes, so let me see how goes this guy. Yes, so I first apply Ry of minus pi over 2. Yes, I will write minus pi over 2. Yes, pi. Yes, after this, I apply Control Z. Yes, and Control Z will do nothing. Yes, so because the first is 0. Yes, so it will go to 0, Ry of minus pi over 2, phi. Yes, and after this, I will apply this guy. Yes, so it will go to 0, Ry of pi over 2, Ry of minus pi over 2, phi. And those cancel. Yes. And if I do with 1, yes, if I start with 1, phi, yes, I will go here. So here is Ry minus pi over 2, phi. Yes, after this, it will go to naught times Ry of minus pi over 2, phi, and will goes to 1, Ry of pi over 2, x, Ry, so this is not multiplication, this is x. Yes, Ry of my pi over 2, phi. And this product, you will calculate, okay, no, not x, it's z here. Yes, so because this is Control Z. Yes, and all this together, what? Now here it is Control Z. Yes. No, but lower I don't never use this gate. So because of this, here, yes. Yes, sorry, yes. Here is Z, and I need to calculate by hands. This matrix is 2 by 2, but 2 by 2 I expect that sometimes is calculated. Yes, then it would be equal to x. Yes, this is no. Por quê? Por quê? Porque sé. Yes, and why this control sign is important? Because you see, I have a diagonal here, and everywhere is 1, except one place in which it is minus 1. And I kind of market this element. I kind of market 1, 1. Yes, the state 1, 1, it is a special state for me, because all others are states, and this revert the sign. And this can be used as a replacement of quantum oracles. Yes, because I can say, okay, if I have this operator, it is the same as value 1, 1 is marked. Yes, this is the answer. Yes, and if I have such operator, yes, then this is the same as 0, 1 is marked. Yes, this corresponds to, this row corresponds to 0, 1. And this is a philosophical state. Yes, because we need to think what is quantum oracle. Yes, and actually creation of such operator is equivalent to creation of quantum oracle. And so this is quite often used. So the next important operator, 2-qubit operator, is swap. So when I have, so this is the formal matrix, but the true meaning is that I have a state AB, and it is moved to a state BA. So they change, they swap. Yes, two qubits. Yes, and remember, this is a reversible operation. Yes, so if you do this, you can do the in opposite direction as well. Yes, so it doesn't contradict. So it is the best analog of copying, yes, information which you have. Yes, because you cannot copy because the copy is not reversible. Yes, but to change is reversible. Yes, so this is what you have. And why this gate is so important? It comes to the devices. Yes, it's come to the physics of the device. Because in any case, qubits are physical objects. And they are somehow located into the space, whatever the word located in quantum mechanics means. And in a certain sense, you can apply, assume controlled knot operation, you can apply operation only to nearby objects. You cannot apply operation to a far enough object. And usually there is, in all quantum computers, there is a connectivity graph. Yes, so you have a qubits, which has numbers, yes? Yes, and some of them are connected, and some of them are not connected. And you actually have much fewer connections than not connections. Yes. And then, but assume that you are a software developer. You don't want to bother yourself with knowing this graph. Yes. And moreover, it changes with every new release. Yes. But you still might want to have a CNOT between 77 and 45. Yes. I mean, what you do. Yes. You say you swap 45 to 44. After this, you swap 44 to 43, and over this pass. Yes, unless you make them neighbor. You apply C0 operator between those, and after this, you start movement back. Yes. Yes. And because of this swap is an important operator. Kind of, it's not possible that you do not have implementation of it on a physical story. Yes, because in another case, if you don't have it, your quantum software developer need to know what is the connection graph. Yes, and this is a problem. Yes, and because of this, because everybody implements swap, yes, and as I told before, yes, swap is nothing, yeah, so any operator is nothing but you choose certain potential, yes, and write and execute like this. Yes, so for some time t, you execute your system. But then if you do this for time t, you can do also this for time t or t half. Yes, and in that case, you will get, for example, square root of swap. So as soon as you physically implement in swap, yes, you implement in square, like you can implement square root of swap as well. Yes, so this is a physical device can do. Yes, and moreover, it can also implement swap to the power alpha. Yes, so I swap is not necessary. Yes, so that's another operator. It's not necessary. It not follows from the fact that you can implement swap, that you can implement I swap. Yes, so if they're equivalent, if they're equal, you don't change them. If they are not equal, you change them and multiply by I. Yes, by imaginary. Yes, so this is the story now. It comes to physics. I don't know why, but quite often for physicists, it's easy to implement this story. I mean, don't ask me why. Yes, because this belongs to physics. Yes, it's not belongs to mathematics. Yes, So this is the story. Yes.
In every single basis, we have the orders equal one, two, one.
Yes. No, but this is for swap. Yes. I mean, this is like, yes, this is because of mathematics of such operators. Yes. So if you have such operator, then any power of this operator, like this. Yes. Yes. No, but oh, this I don't know. Okay, this okay. Don't. I mean, there are so many beautiful math statements, yes, and I refer like to beautiful mathematical proofs. So there is a book which has a name, Proofs from the Book, which has a kind of exactly very nice collection of very nice mathematical ideas with something like this. Yes, so you can be inspired by Ramanujan, who have a lot of statements. But I mean, don't overthink about it. Actually, like, for me, it is important now the following. Yes, so with C0 gate, I can implement any 2-qubit operation. Yes, okay, I need swap because I want not to know about connectivity graph. Yes, and all the rest is just, you know, how to say, it's a bit of play. Yes, so it doesn't has effects to the true algorithm, to true story. Yes, but I need to say this because I hope that my course is interesting for you. So you will go to the internet and read by yourself something, yes? And it might happen that you will say that, okay, it is implemented ISWAP, say nothing about C0, yes? And you will start to ask, why teacher didn't say this? Yeah, I mean, it can put you into confusion. Yes, so because physical implementation, it's physical implementation. Not all computers implement controlled not as a basic element. Some of them implement square root of swap as a basic element. Some of them implement ISWAP as a basic element. There would be one more gate which some computers use. I will show in further slides. Yes, so this. Let's play a bit, even that the time is finishing, but we started a bit later. Yes, so let's do this. Yes, so what represents this operation? Not C, C not, C not. Yes. What how to say? What it is? Yeah, what it would be? No, but remember, operators are not commuting. You cannot change the order of those two. Okay, let me, how to say, demonstrate that it's not possible to do like this, so you cannot cancel those operators. Let me show why. Yes. What? No. Let me see how this thing acts on the state 0, 1. Yes. So how would act the first C0? It will do nothing. Yes. So C0. Yes. How would act not C? It will revert the first qubit. And so you will get 1, 1. And how will act the last one? It will revert the second qubit. So you will get 1, 0. Yes, and so here there was no action, and here there was action. So it's not correct that you can erase those two guys. What? They do not. Yes, okay. Let us see. Okay, we started with 0, 1, and we'll get 1, 1. Yes, it's a C not and not C. But now let us do 0, 1, apply not C to it. Yes, what it would be, not C to it. It will be 1, 1. Yes. And after this, we apply C naught. Yes, it will be 1, 0. Because now this was 1, so we should apply not to a second. To the second. Yes, so not C, 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 C naught do not commute. Yes. Yes. No, 0 stays 0. Yes, because when you do control not, the first qubit never changes. Yes, and the second changes is if the first one was 1. Yes, so there is no action. There is action of not C.
As 0, 1 is right now at the column, the first one would be A and the second one would be B. But
No, 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 no. No, 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 no. Oh, okay. This is important and notion. Also, how I will write 0, 1 as a column. Yes. It's a column on 4 vectors. Because I should write it in the form. It's 0 times 0, 0 plus 1 times 0, 1 plus 0 times 0, 1 plus 0 times 1, 1. So this is the notation. It would correspond to a vector 0, 1, 0, 0. So it's important that when I write like this, if I would like to write it in a vector notation, this is a 4-dimensional vector. Yes. So then if I would apply matrices, yes, I should apply matrices, 4-dimensional matrices. But, yes, I told that multiplication of matrices is a hard job. All of us are human. Yes, so we make mistakes. Yes. So because of this, I recommend to follow another story. Yes? So I looked on a basis state and see how each of those, what is the image of this basis state under each of those operations. Yes, and here I apply C naught, and by definition of C naught, 0, 1 goes to 0, 1. Yes, so we had this. Yes, I apply not C for this thing, so the second always stays, because I mean now controlling is the second. Yes, so it always stays, and because it is equal to 1, the first one should change. So it goes to 1, 1. Yes, and after this I apply to 1, 1 C naught, yes, which is by the table of C naught, by definition of C naught, yes, which goes to 1, 0. Just so and if I combine all together, that I will get that 0, 1 goes to 1, 0. Let us now see how acts on 0, 0. Yes, just let us not try to guess, yes, but let us just, do a hard job. Yes. So 0, 0 by C naught goes to 0, 0. Yes, because the first qubit is 0, so nothing is changed. C naught, so 0, 0, after this we apply not C, it goes to 0, 0. And after this we apply once again C naught, it goes to 0, 0. Yes. Now let us do 1, 0. Yes. Then by C naught, it will goes to 1, 1. By not C, it will goes to second is 1 because it is copied, and the first one should changes. So 0, 1. And by C naught, the first is copied as 0, and the second doesn't change because the first is 0. Yes. So now the last thing. Yes. So 1, 1 goes by C naught goes to 1, 0. By not C, to 1, 0, and by C naught, one, 1. Great. Yes. So now summarizing what we have. 0, 0 goes to 0, 0. Yes. Yes. Have we seen such an operation? Have we seen such an operation? What matrix? Its matrix becomes yes. So this is swap. Yes, this is change of two qubits. Yes, but I hope that they implement it inside not like this, because this is a hard operation. And the true story that there are a lot of relation. So I mentioned to you some operators, yes, during this. There are a lot of statements that how you can represent one over others. Yes, so here I related square root of swap and C naught. Yes, but I mean just remember that via any of those two is relation. Yes, and I suggest, so let me see what is the next slide. Yes, I suggest to finish today now, yes, and and let us continue next Tuesday. Questions from the Zoom?
All good here.
Okay. So then finish. Yes, and